All right, just look around you for a second. Chances are something nearby is spinning. Maybe a fan, a wheel, the hard drive in your computer. It seems so simple, right? But hidden inside that motion is a secret geometry, a really precise science that basically keeps our world from flying apart. So today, we're going to dive into that hidden world. So this sounds like the start of a weird riddle, doesn't it? What in the world could a massive power turbine, a rugged tractor drive shaft, and a super delicate surgical nail possibly have in common? Well, the answer is a fundamental principle of geometry that, quite literally, keeps our world running. You see, at the heart of all these things is the good old rotating shaft. We see them everywhere, and they look incredibly simple. It's just a metal rod spinning around. But that simplicity, it's a total illusion. What we're actually looking at is a marvel of precision engineering. That's because every single tiny detail of that rod's geometry, I'm talking its length, its thickness, its exact shape, that's what makes the difference between smooth, efficient operation and a complete catastrophic mechanical failure. The stakes are, incredibly high. So what's the big problem that engineers are always trying to solve here? Well, it has to do with what happens when you spin something really, really fast. Let's meet the villain of our story. And the villain's name is critical speed. Okay, think about it like this. You're pushing a kid on a swing. If you push at just the right rhythm, that's its resonant frequency, the swing goes higher and higher with almost no effort. Now just imagine that swing is a steel shaft spinning thousands of times a minute. At its critical speed, even the tiniest imbalance gets amplified into this violent, uncontrollable vibration. And this chart really lays it all out. These are the two states of being for any spinning shaft. Below its critical speed, everything is great. It's stable, it's predictable, super efficient. But the moment it hits that critical speed, it becomes dangerously unstable. So the entire goal for an engineer is to design the machine so its normal operating speed stays safely away from that dangerous zone. So how do they do that? How do they tame this beast of vibration? Well, their number one weapon is geometry. By carefully shaping the shaft, they can actually change its critical speed and make sure it stays in that safe, stable zone. And the relationship here is actually pretty straightforward. A thicker shaft is a stiffer shaft. It's kind of like a guitar string. A thicker string makes a higher note because it has a higher natural frequency. It's the exact same idea for a shaft. A stiffer one has a higher natural frequency, which means you can spin it much, much faster before it hits that dangerous critical speed. But of course, thickness is only half the story. Where you put the supports, the bearings, is just as important. As you can see here, when the bearings are spaced really far apart, the shaft gets more flexible. It's almost floppy in the middle. This lowers its stiffness and dramatically cuts down the safe speed it can handle before it starts to vibrate. And this whole process just goes to show you that modern engineering is anything but guesswork. It all starts with the fundamentals, basic physics calculations to get a starting point. Then, from there, they create what's called a digital twin, a perfect 3D model that they can use for simulations. Then the real work starts, this cycle of iteration, of tweaking the diameter here, shifting a bearing there, testing and retesting, over and over, until the geometry is absolutely perfect for the job. But, of course, the real world is never that perfect, is it? So what happens when shafts aren't solid? Or what about when they have microscopic cracks or bends, from the manufacturing process? Well, engineers have to design for these imperfections too. Take a hollow shaft, for instance. Hollowing it out makes it more flexible and actually reduces its stiffness, which sounds like a bad thing, but it also dramatically reduces the mass. And in things like aerospace or high-performance cars, getting rid of weight is absolutely everything. So this trade-off is often a really brilliant engineering solution. 40%. Just hold that number in your head for a second. What on earth could be so sensitive that a 40% deviation means total failure? The answer? Precision seals. In some super high-tech machines, they have these seals that use magnetic fluid, and the gap they operate in is microscopic. If the shaft wobbles or is off-center by just 40% of that tiny gap, the seal fails. It just shows you the incredible level of geometric precision we're talking about here. And the complexity, it just keeps piling on. Engineers have to model the exact angle of the shaft, the potential for tiny cracks, the shape of every single opening, and the precise placement of every gear or coupling that's attached to it. I mean, as you can see from this list, every single geometric detail has an impact. So let's bring all this out of the theoretical and into the real world. Because this isn't just about engines and turbines. These principles of geometry, they apply at every single scale, from massive construction projects right down to the human body.
And this is really where it all comes together. The stability of a crane in the wind, the power delivery in a tractor, the success of a surgery that uses a femoral nail, even the safety of a long-span bridge, all of it comes down to getting this hidden geometry exactly right.
Just look at these examples. For that femoral nail in your leg, the radius of curvature is everything. I mean, think about it. The human femur isn't a perfectly straight stick. It has a natural curve to it. The nail has to match that curve perfectly to be inserted without, puncturing the bone. And for a huge bridge, the geometry of the main support has to be streamlined to stop the wind from causing catastrophic vibrations. It's the same principle, just a totally different application. And that really is the bottom line. In engineering, shape is function. It's not about making something look good. It's about making something work, period. The hidden geometry is what dictates whether something succeeds or fails. So I'll just leave you with this question. The next time you see a fan spinning, or a wheel turning, or a propeller moving, I hope you'll see more than just a simple rod. I hope you'll see the hidden, elegant, and absolutely critical geometry that makes it all work.